Hi, in this video we're going to talk about exponential functions in a little more in depth. We're going to talk about exponential functions with what I like to refer to as a change in the period, which is the amount of time it takes for one iteration of change to occur. It assumes a couple of things. It assumes that you understand that the general form of an exponential is y equals ab to the x, where a is the initial value and b is the multiplier. Okay? And it assumes you're comfortable writing one of those in a simple situation. So this is a little more phase 2 in terms of what we see with exponential functions. Okay, I'm going to look at 3 scenarios that are very similar. I'll read them in a second. There's just a subtle difference in each problem that you'll see as I read them. That subtle difference is going to have a tremendous impact upon how we write the exponential function of the form y equals ab to the x. Okay? So, before we go into this any further, there's something that you always have to keep in mind when dealing with exponential functions. And you need to realize that the exponent in an exponential function is representative of the number of changes on the initial value. Okay? This is something that can be very helpful when you get bogged down in a problem that has these weird changes with time, where it's a little hard to figure out how to manipulate the exponent when you're writing it. Okay, so these have a certain feel to them, but that feel is guided by this statement that the exponent is equal to the number of changes. If you can keep that in mind, it'll make sense when you write the exponent part of an exponential function, if it's a little bit of a weird exponential function. Okay, so let's take a look at this first problem, where it says a colony of bacteria increases by 20% every day. If it starts with 5,000 bacteria, what is the exponential function that tells the amount of bacteria y at a given number of days x? Okay. The next problem is identical with regard to the first one, with one exception. It's not saying that the increase is happening by 20% every day. It's 20% every 6 days. And in this last one, again, although we do have a 20% increase on the same initial value of 5,000 bacteria, it's not happening every day or every 6th day. It's happening 6 times a day. Well, these are subtle differences that have tremendous impact on what we write. Okay? So I'm trying to put some focus on these and try and help you through them. Okay, so the first one's decently easy, okay? I just need to be able to identify the initial value of A and the multiplier to start, and then we'll see how that progresses from there. So A is going to be 5,000, and it's the case in all 3 of these problems because it's the initial value of bacteria. And then in all 3 of these problems, we see that there's a 20% increase, which means we get 100% plus 20% equals 120%, making the multiplier in decimal form 1.2. Okay? So we know that 1.2 is going to be equal to our b value. Okay? So when I go to write this first function, where y is the number of bacteria and x is the number of days, it won't be too hard because, in fact, you're getting one change per 1 day. Okay? So when we talk about the days going by, there's a 1-to-1 ratio between the days and the changes. Well, this is important, okay? Because here when we say x is the given number of days, we have to make sure that we're putting in a number of days, but it's translating to a number of changes. Well, it's very easy because, like I said, it's 1 change per day. It's very straightforward. So we will write y equals a, which in this case was 5,000, times the multiplier of 1.2 to get a 20% increase, and then the exponent is just going to be x. But I want us to look at this a little more closely and make sure that you realize that this statement is held to be true. Okay? That the exponent equals the number of changes. Okay? Well, here it says that x is going to be equal to days. Well, this should jive together pretty well. Because if I talked about x being 3 days, I would plug in 3. And this would represent the number of changes as well, because it's 1 to 1. When you put in 3 for days, the exponent is 3, and 3 is the number of changes. Similarly, in 7 days, if you plugged in 7, the exponent would be 7. And this makes sense because in 7 days, there are 7 changes. So this is definitely a straightforward type of idea. There's nothing to fiddle around with in terms of the exponent when we say it's every day, because again, it's a 1 to 1 ratio between the changes and the days. However, when we get to the second example where it says every 6 days, this is going to be a little different. So the part of the problem that's the same still, it's going to be y equals the initial value of 5,000 times 1.2 as a multiplier. But then it brings into question, what is the exponent? Well, again, the exponent's going to be the number of changes. But here it says that x is the number of days. So there's not this 1 to 1 relationship because I'm not getting a change every day. I'm getting a change every 6 days. Okay. Well, it would make sense to me, though, if I were to put in, just by experiment, if I were to put in 6 for my days, that wouldn't be good because it would also mean that I'm getting 6 changes, which isn't true. So the question here is, how do I turn this 6 into a 1? Because the 6 representing the days needs to create an exponent of 1 for the changes. Well, you probably have figured it out already. I guess it's divided by 6, because 6 over 6 is going to give me 1. This is legit because in 6 days I get 1 change. Similarly, if I were to put in 12 days, which is 2 periods of change, I would want an exponent of 2. So putting in 12 would be legit as long as I divided it by 6, because that would create an exponent of 2, which makes sense because after 12 days, you're getting 2 changes. So although we're putting in a number of days, the entire exponent has to be representative of the number of changes. Well, if you just saw what I did there was I took any number of days that I had and divided it by 6. So this makes the right relationship, establishing that the exponent is the number of changes. Now the exponent here is not days, because that's just the top part of the exponent, the numerator, because it says x is days. So again, it stands up to that test of if you just take a simple multiple of 6, something like 24, and you plugged in 24 days, well, it would make sense to me that if in 24 days divided by 6, there would be 4 changes. So again, I'm still plugging in days for x, but the entire exponent is representative of the number of changes. So that's a legit expression there. So again, it's got some feel to it. You have to think while you're writing it. So what do we have here in this next example? Something a little different here. It says a colony of bacteria increases by 20% 6 times a day. Okay, well, we still have the same initial value, and we still have the same multiplier. So we're still going to get 5,000. Sorry, get better color code for consistency. Y equals 5,000 times a multiplier of 1.2. And then this question of what is the exponent, so that I can plug in x for days, but talk about it being the number of changes. Well, I just need to think about that for a second. Because if I put in 1 day, this would not be good just as is, because when I plug in 1, I have to turn the exponent somehow into the number of changes. Well, 1 day is supposed to get me 6 changes, so how do I turn 1 into 6? Well, I guess I can multiply it by 6. Similarly, if I had 2 days and something changed 6 times a day, that means I would have to take this 2 and convert it to a 12 somehow. Well, I could do that by multiplying it by 6. And similarly, I guess if I had something like 5 days, in 5 days, you would get 30 changes because there's 6 changes per day. So I guess decently easy enough to understand. If it's 6 changes per day and you have x days, it's just going to be 6x. So this makes sense. That again, all three of these have something in common, and that's that the exponent is equal to the number of changes, still respecting the fact that x in all three problems is equal to the number of days. So all the input is the number of days. The entire exponent reflects the number of changes that occur after those days have happened. So I hope that this is a lesson in how to sort of adjust the exponent. There's times where you have to adjust the exponent using addition or subtraction. They're pretty intuitive, so I wanted to focus on these changes in period to the exponent in a way that involved multiplication and division, because they take a little more thought. But again, don't forget that mantra that the exponent has to reflect the number of changes, and you need to be careful when there's an odd period of time involved where it's not a one-to-one relationship in terms of the number of changes and the number of days or years or months or whatever your measuring goes by. So I hope this is a help, and enjoy. Feel free to watch it again. And it takes a little practice, but with thought while you're doing it, you can get these answers to make sense and hopefully become an intuitive part of how you approach exponential functions.